Hi, welcome back to Easy Math with Dr. Nasir, your path to math confidence. Please share my lectures with others and don't forget to subscribe my channel so you never miss a conceptual concrete lesson. Well, in today's lecture, we will see initial value problems consisting of second order linear ODEs and initial conditions. Well, see a theorem. An nth order homogeneous linear ODE an of s dn y by dxn plus an minus 1 of s dn minus 1 y by dxn minus 1 plus up to a1 of x dy by dx plus a naught of x y is equal to 0, where s belongs to I subset of R, and a j are functions from I to R and j varies from 0 to n, and an of x is non-zero for s belongs to I. Possesses linear independent solutions I varies from 1 to n on I. Further, their linear combination y of x is equal to c1 y1 of x plus c2 y2x up to cn yn of x, where s belongs to I, and ci are arbitrary constants I varies from 1 to n, is known as a general solution of the ODE on I. Well, see fundamental set of solutions. The set of linear independent solutions I varies from 1 to n for the homogeneous linear nth order ODE on I is called the fundamental set of solutions for the homogeneous linear nth order ODE on I. Let's see an exercise. The two-parameter family of functions y of x equals c1 exponential x plus c2 exponential minus x, where s belongs to R, is the general solution of the ODE d2y by dx square minus y is equal to 0, where s belongs to R. Find a member of the family that satisfies the initial conditions y of 0 is equal to 0, dy by dx of 0 is equal to 1. Well, see solution. Consider y of x equals c1 exponential x plus c2 exponential minus x, where s belongs to R. Differentiating, we have dy by dx of x equals c1 exponential x minus c2 exponential minus x, where s belongs to R. Now, using the given initial conditions 1.1, we have y of 0 is equal to 0, dy by dx of 0 is equal to 1. So c1 exponential 0 plus c2 exponential minus 0 is equal to 0, and c1 exponential 0 minus c2 exponential minus 0 is equal to 1. So c1 plus c2 is equal to 0, and c1 minus c2 is equal to 1. Well, solving this for c1 and c2, we have c1 is equal to 1 by 2, c2 is equal to minus 1 by 2. So the required solution of the ODE satisfying the given initial condition is y of x is equal to 1 by 2 exponential x minus 1 by 2 exponential minus x, where s belongs to R. So y of x is equal to sine hyperbolic x, where s belongs to R. Well, see another exercise. The family of functions y of x equal to c1 exponential 4x plus c2 exponential minus x is the general solution of the ODE d2y by dx square minus 3 dy by dx minus 4y is equal to 0, where s belongs to R on R. Find a member of the family that satisfies the initial conditions y of 0 is equal to 1, dy by dx as 0 is equal to 2. Well, see solution. Consider y of x equal to c1 exponential 4x plus c2 exponential minus x, where s belongs to R. Differentiating, we have dy by dx of x is equal to 4c1 exponential 4x minus c2 exponential minus x, where s belongs to R. Now, using the given initial conditions 1.2, we have y of 0 is equal to 1, dy by dx of 0 is equal to 2. So we have c1 exponential 4 into 0 plus c2 exponential minus 0 is equal to 1, and for c1 exponential 4 into 0 minus c2 exponential minus 0 is equal to 2. So c1 plus c2 is equal to 1, and for c1 minus c2 is equal to 2. Well, solving this for c1 and c2, we have c1 is equal to 3 by 5, c2 is equal to 2 by 5. So the required solution of the ODE satisfies the given initial conditions is y of x equal to 3 by 5 into exponential 4x plus 2 by 5 into exponential minus x, where s belongs to R. Well, see another exercise. The family of functions y of x is equal to c1x plus c2 x log x is a general solution of the ODE s square d2y by dx square minus s dy by dx plus y is equal to 0, where s belongs to R other than 0. On the open interval 0 to plus infinity, find a member of family that satisfies the initial conditions y of 1 is equal to 3, dy by dx of 1 is equal to minus 1. Well, see solution. Consider y of x equal to c1 x plus c2 x log x, where s belongs to 0 to plus infinity open interval. Differentiating, we have dy by dx of x is equal to c1 plus c2 plus c2 log x, where s belongs to 0 to plus infinity open interval. Now, using the given initial conditions 1.3, we have y of 1 is equal to 3, dy by dx of 1 is equal to minus 1. So c1 plus c2 into log of 1 is equal to 3, and c1 plus c2 log of 1 is equal to minus 1. So C1 is equal to 3 and C1 plus C2 is equal to minus 1. Well, solving these for C1 and C2, we have C1 is equal to 3 and C2 is equal to minus 4. So the required solution of the ODE satisfying the given initial conditions is YOS is equal to 3x minus 4x log x, where x from 0 to plus infinity open interval. Well, see another exercise. The family of functions YOX equal to C1 plus C2 cosine x plus C3 sin x is a general solution of the ODE d3y by dx cube plus dy by dx is equal to 0, where x belongs to R on R. Find a member of the family that satisfies the initial conditions y at pi is equal to 0, dy by dx at pi is equal to 2, d2y by dx square at pi is equal to minus 1. Well, see solution. Consider YOX is equal to C1 plus C2 cosine x plus C3 sin x, where x belongs to R. Differentiating, we have dy by dx of x equals minus C2 sin x plus C3 cosine x, where x belongs to R. Again differentiating, we have d2y by dx square of x equal to minus C2 cosine x minus C3 sin x, where x belongs to R. Now using the given initial conditions 1.4, we have y at pi is equal to 0, dy by dx at pi is equal to 2, d2y by dx square at pi is equal to minus 1. So C1 plus C2 cosine pi plus C3 sin pi is equal to 0, minus C2 sin pi plus C3 cosine pi is equal to minus C2 cosine pi minus C3 sin pi is equal to minus 1. So we have C1 minus C2 is equal to 0, minus C3 is equal to C2 is equal to minus 1. Well, solving these for C1, C2 and C3, we have C1 is equal to minus 1, C3 is equal to minus 2, C2 is equal to minus 1. So the required solution of the ODE satisfying the given initial conditions is YOX is equal to minus 1 minus cosine x minus 2 sin x, where x belongs to R. Well, see another exercise. The two parameter family of functions YOX is equal to C1 plus C2 x square, where x belongs to R, is a family of solutions of the ODE as d2y by dx square minus dy by dx is equal to 0, where x belongs to R. Show that constants C1 and C2 cannot be found so that the member of the family satisfy the initial condition of y at 0 is equal to 0 and dy by dx at 0 is equal to 1. Explain why. Why this does not violate theorem 4.1.1. Well, see solution. Since the solution satisfies the given ODE, so from the given ODE we have dy by dx at 0 is equal to 0. This violates the given initial condition. So the constants C1 and C2 cannot be found such that a member of the family of solutions satisfy the given initial conditions y at 0 is equal to 0 and dy by dx at 0 is equal to 1. This does not violate theorem 4.1.1 as coefficient of d2 by dx square, that is a2x is equal to x vanishes for x is equal to 0. According to theorem 4.1.1, the coefficient of d2 by dx square must be non-zero at every point from the domain of the solution. Well, see another exercise. Find family of the two parameter family of solutions y is equal to C1 plus C2 x square, where x belongs to R, of the ODE as d2 by dx square minus dy by dx is equal to 0, that satisfy the initial conditions y at 0 is equal to 0 and dy by dx at 0 is equal to 0. But see solution. For y at 0 is equal to 0, we have C1 plus C2 into 0 square is equal to 0. So C1 is equal to 0. So yx equal to C2 x square, where x belongs to R. Differentiating, we have dy by dx of x equal to C2x, where x belongs to R, which satisfies initial condition dy by dx at 0 is equal to 0 for an arbitrary C2 belong to R. Thus, the required family of solutions satisfying the given initial conditions is yx equal to C2 x square, where x belongs to R and C2 is the arbitrary constant. Well, see another exercise. The two parameter family of functions x of t is equal to C1 cosine omega t plus C2 sin omega t is a general solution of the ODE d2 x by dt square plus omega square x is equal to 0, where t belongs to R and omega is non-zero on R. Find a solution satisfying the initial conditions x of 0 is equal to x0 and ds by dt at 0 is equal to x1. Well, see solution. For the initial condition x at 0 is equal to x0, we have C1 cosine omega into 0 plus C2 sin omega into 0 is equal to x0. So C1 is equal to x0. Now differentiating 1.5, we have ds by dt of t is equal to minus C1 omega sin omega t plus C2 omega cosine omega t, where t belongs to R. Now using the initial condition ds by dt at 0 is equal to x1, we have minus C1 omega sin omega into 0 plus C2 omega cosine omega into 0 is equal to x1. So C2 omega is equal to x1. So C2 is equal to x1 over omega. Thus, x of t is equal to x naught cosine omega t plus x1 over omega sine omega t, where t belongs to R, is the required solution. Well, see another exercise. The two-parameter family of functions x of t is equal to c1 cosine omega t plus c2 sine omega t is the general solution of the ODE d2 x by dt square plus omega square x is equal to 0, where t belongs to R and omega is non-zero on R. Find a solution satisfying the initial conditions x of Find a solution satisfying the initial conditions x at t naught is equal to s naught and dx by dt at t naught is equal to s1, where t naught belongs to R. Well, see solution. Differentiating 1.6, we have dx by dt of t is equal to minus c1 omega sine omega t plus c2 omega cosine omega t, where t belongs to R. Now, using the given initial conditions, we have c1 cosine omega t naught plus c2 sine omega t naught is equal to x naught and minus c1 omega sine omega t naught plus c2 omega cosine omega t naught is equal to s1. So we have c1 cosine omega t naught plus c2 sine omega t naught is equal to s naught and minus c1 sine omega t naught plus c2 cosine omega t naught is equal to s1 over omega. Well, solving these for c1 and c2, we have c1 is equal to s naught cosine omega t naught minus s1 over omega sine omega t naught and c2 is equal to x naught sine omega t naught plus s1 over omega cosine omega t naught. Thus, x of t is equal to x naught cosine omega t naught minus s1 over omega sine omega t naught into cosine omega t plus s naught sine omega t naught plus s1 over omega cosine omega t naught into sine omega t, where t belongs to R, which is equal to x naught cosine omega t naught minus s1 over omega cosine omega t sine omega t naught plus x naught sine omega t naught plus s1 over omega sine omega t cosine omega t naught, where t belongs to R, which is equal to x naught cosine omega t naught plus sine omega t naught plus s1 over omega into sine omega t cosine omega t naught minus cosine omega t sine omega t naught, where t belongs to R. Now, using trigonometric identities, cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta, where alpha and beta belong to R, and sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta, where alpha and beta belong to R. We have x of t is equal to x naught cosine omega into t minus t naught plus s1 over omega sine omega into t minus t naught, where t belongs to R, which is the required solution. Let's see another exercise. Find an interval centered above 0 for which the initial value problem x minus 2 into d2y by dsk plus cy is equal to x, where x belongs to R other than 2 and y at 0 is equal to 0 and dy by dx at 0 is equal to 1 as a unique solution. Well, see solution. The required interval is I is equal to minus 2 to 2 open interval. Well, see another exercise. Find an interval I centered above 0 for which the initial value problem d2y by dxk plus tangent x into y is equal to exponential x, where x belongs to R other than 4k plus minus 1 into pi by 2, where k belongs to z, and y at 0 is equal to 1 and dy by dx at 0 is equal to 0 as a unique solution. Well, see solution. The required interval is I is equal to minus pi by 2 to pi by 2 open interval. That's it for today. Well, in the next lecture we will see more exercises. Don't forget to share, like and subscribe my channel Easy Math with Dr. Nasir.